Hello everyone and welcome back to another Howard Science video. This video is our required practical for physics and it's about the resistance in a wire, which forms one of the practicals for P4 on electric circuits. So what we're going to do today is have a look at how we can test the resistance in a wire as the length of the wire changes. So to do that I'm going to need a piece of wood which has been measured to 1 meter and it has a piece of constantan wire on it, or it could be nichrome. The other thing I'm going to need to have is an ammeter, a voltmeter and 5 wires. And 2 crocodile clips. The first thing I'm going to need to do is build a series circuit involving the ammeter. So the current is measured in series and the potential difference or voltage is measured in parallel. So what I've done is I've connected the positive end of the circuit to this crocodile clip, and I've connected the negative terminal to the negative end of the ammeter, and the positive terminal is going to have the other crocodile clip on. Now I'm going to increase the length in 10 centimeter intervals up to 80 centimeters. So the first setting I'm going to do is put my crocodile clip on 10 centimeters, and my second crocodile clip is going to go at 20 centimeters, and that will then give me a distance of 10 centimeters, which will be the first reading. Now, so the first thing I'm going to do is check that the current is going through the circuit, and as you can see, there is a reading on the ammeter. Okay, so the next thing I need to do is measure the potential difference, and the potential difference will be measured across the component, in this case the 10 centimeters of wire. So I now need to connect my voltmeter across, and I'm going to connect it into the wires that are above here, and I'm now just going to check to see that I get a reading on my ammeter and my voltmeter, and I do. Okay, so now we're ready to start. The key thing about this practical is to ensure that we get repeatable results. So that means that we can do it again and again with the same equipment as investigators and get the same value. So what I'm going to do is I'm going to use a timer to get a 3-second countdown. And when I get the 3-second countdown, I record the value for the current and the potential difference. And I will then do that 3 times and then calculate an average before I move the length of the wire to the next setting, which will be 20 and 30 up to 80 centimeters. It's also important that we don't leave the wire on for too long, because the wire will heat up as the electrons pass, the wire will increase in temperature. And in order to get the most accurate data, we have to do it where the temperature of the component remains as constant as possible. So let's start the practical, and I'm going to switch it on, and I'm going to use the timer to help me get a 3-second countdown and record the current and the potential difference. So here we go. 3, 2, 1, and I read it. So that's 0.93, and the voltage and potential difference was 2.03 volts. Then I switch the power supply off, and then I do it again. 3, 2, 1, read, and that's 0.92 and 2.03 volts, and switch it off, and then I get my third repeat. 3, 2, 1, read, and that's 0.93 amps and 2.04 volts. Then I switch the power supply off, and now I then unclip my crocodile clip and move it to the next length here. So that's now a length of 20 centimeters, and I repeat the practical again, and I continue that process up to 80 centimeters. Now, a couple of quick considerations. Where do you place the crocodile clips? It's important that you either place them on the mark, to the right of the mark, or to the left of the mark, but you must be consistent, otherwise the length will change. As I've already mentioned, it's important that we don't leave the power supply on for too long, because we don't want to heat up the wire. The other thing for safety is to ensure that we have it on a low voltage on the power supply. We wouldn't be setting this to 12 volts, for example, because too much current will pass through the wire and we may end up with a fire or burn hazard. Okay, so now that the practical's done, now I can start processing my results. So to do that, I'm going to need to use the equation V divided by I is equal to R, which is Ohm's law. So the first potential difference for 10 centimeters was 2.03 average divided by 0.92 amps, which comes out at 2.21 ohms. And for 20 centimeters, it would be 2.23 volts divided by 0.52 amps, which equals 4.29 ohms. What I then need to do is do the same for the other 6 results and plot a graph of resistance on the y-axis, which is the dependent variable, divided by the length of the wire in centimetres, which is the independent variable. From that, I can then decide if there is a relationship, and if so, what is it? Okay, so now I've plotted my graph of the length of wire along the x-axis and the resistance of the wire on the y-axis. And as you can see, I've got data that appears to be forming a straight line. The data is a little bit problematic in one or two places. Maybe you could suggest why that might be. Well, one of the reasons is because I was doing the practical on my own, it was difficult for me to judge exactly what the correct potential difference and current values were. As a result of that, I may have underestimated or overestimated, which is why it's good to do the practical in pairs. The other way to do it may have been to have filmed the practical, and when the timer reached the required value, you could have then slowed it down and read what the current and potential difference were at those times. But as you can see, I've managed to get a straight line. I've considered all of the points, and the fact that it is a straight line going through the origin means that we can then determine that yes, it is linear, and yes, there is a positive correlation between the length of the wire and the resistance. So if we were asked a question on what is the relationship between the length of the wire and the resistance, we can say that as the length of the wire increases, the resistance increases as well. But because it's a straight line going through the origin, we then need to check to see whether or not this is a directly proportional relationship. So to do that, we need to test such a thing. So for example, what is the resistance of the wire at 20 centimeters? To do that, I would need to place my ruler at 20 and draw a line going up. Now, where it hits the line of best fit, not the point, but the line of best fit, I'm then able to draw a line going across. And as you can see, the length of wire at 20 gives a resistance of about 4.15 ohms. And what I then need to do is see, well, if I increase the length of the wire to 40, i.e. multiplying the length by 2, i.e. doubling the length, what does that do for the resistance? Well, I can then place my ruler at 40, draw a line going up, and where it hits the line of best fit, not the point, but where it hits the line of best fit, I'm then able to draw a line going across and read off that value. And as you can see, it comes out at 8.30 ohms. So pretty much double the length, you double the resistance, and this is what's known as direct proportionality. And that's what Ohm's law actually says for a wire. A wire is ohmic, and we use the term ohmic to describe the fact that as long as the temperature of the component, in this case the wire, remains constant, if you are to double the length, then you will double the resistance. And this proves that a wire is an ohmic conductor as long as the temperature remains constant. So that concludes the practical to do with length of the wire and how it affects the resistance.